Thanks for the introduction. I'm pleased to present this collaborative work with Matthew Sutton, my ex-PhD student, and Pierre Lafayette de Michaud. And I will present some works in the family of PLS. So just to give some idea which data we can deal with our different packages. So we have two blocks of data, and we want to have some data integration works on it. So to link these two blocks of data, so I put you some example. So we work on omics data, so we can think that the Y block of data is some gene expression, and the X block of data is some SNP data. And you want to have some link between the gene expression and the SNP data. In the neuroimaging field, you can imagine that the Y matrix is behavioral variable and the X is some brain activity. In neuroimaging genetic, which is a hot topic, is to combine information in genetic part and in the imaging part. And in ecology, because I work in ecology now, so in the Y part you can see that is water quality variable, and X is some variable which describes the landscape. So in this kind of example, we will use some PLS. You can use some PLS, and in different kind of shape of the data. So when we talk about big data, we have different shape of data. So this is quite, you know this, but in our package, we can deal with different kind of shape of the data. So wide data, tall data, and tall and wide. So for the wide data, which is more appear in genomics, so you have more variable than observation. So you have some trouble with classical approach, and you have sometimes you do some overfitting. So you need to regularize or to do some variable selection. In the tall data example, you have a lot of observation and some variable, but the most tricky part is the computational aspect and the memory aspect in R to deal with this. And of course, the more challenging part is tall and wide data, and so you need to use some trick to deal with this kind of data. So a lot of variable and a lot of samples. So you need to use some trick like divide and recombine approach and so on. So I will start first by, because I have 30 minutes, is it? No, it's a joke, okay. So we will start by the wide data, so high dimensional data we call also in genomics. And the main constraint in genomics, you have more variables than observation, and you have also a lot of collinearity in your data. So to deal with this, our contribution also in this part was this kind of data is to incorporate some knowledge in the data structure and to incorporate the group structure in the data. Because when you add more information, you will improve your interpretability and also your prediction. So in this context, for example, I'll give you an example. In the genomics, you have some genes which can belong to some pathway because they might act together to regulate the biological system. So we want, for example, to detect more the pathway than the individual. So I give you some example. You have some SNP data, and the SNP are grouped into genes. But you can also get some gene expression data, and the genes are grouped into pathway. So we have this structure in the data. So we include this group structure in our algorithm. So to be visualized, so we have the X matrix, is just an example, and the Y matrix, with the Y is the phenotype, so it's a multivariate response variable, and the X is your predictors. But it's grouped, you have a group structure. So you want to select the group, so all the variables into the group are selected or not selected. Or you also want to do some sparsity within the group. So maybe some groups are useful to explain the multivariate phenotype, why, but inside the group, you want also to do some sparsity, so some within sparsity. So we have developed some different approaches, and I give you some advertisement. So you have the first article in bioinformatics, and the package associated is sparse group PLS, so sparse group partial least square. And we have recently extended this work by adding one more layer. So For example, I give you an example. The SNP belong to the genes, and the genes belong to the pathway. So we have developed the sparse group subgroup PLS. Oh, it's nice. Okay. So, and now it's called SGS-PLS, and is available on the GitHub, the package on the GitHub of Matthew. Okay, and just to get the main idea is to write the optimization problem of the PLS, and after to add some penalties, like the L1 penalty and the L2 penalty, to have the group and the individual. Okay, so why is the PLS? Why is the PLS? Because the PLS, you can use the PLS in two ways, in the symmetric situation and the asymmetric situation. Symmetric situation, you want to analyze the association between the two blocks of data. You don't care about what is Y and what is X. You can put X there, Y there, on the back, on the front, everywhere, okay? So symmetric situation. And asymmetric, you have X is a predictor and Y is your response variable. So there are the two ways in the PLS you can use the PLS. Okay, so the partially square is, you can see this as a supervised version of the PCA. So it works by constructing some pairs of latent variables. And a latent variable is just a linear combination of all your matrices. So you have your X matrix, you do dimensionalization by doing a linear combination of all your variables. And the Y matrix, similar. And the pairs is, as the first linear combination, are the most correlated to the linear combination of the Y part. So this is a pair of latent variables. This is like the PLS is working. Okay, some mathematics now. How it works? So how it works, but the family of the PLS is a lot of different PLS. There's the PLS-C, the PLS mode A, the PLS mode B, the PLS-R. We don't know what is after. Okay, so many different PLS. Most of them are in the symmetric situation, and the last one, is in asymmetric. But the good thing, different optimization function to optimize, but the good news, this is the good news today, is all is based on the SVD, the singular value decomposition. So now you want to do what you know is SVD. SVD is just for any matrix. You can decompose the matrix of R by the product of three matrices which have nice properties, U, delta, and V. And U and V are orthonormal matrices, and delta is a diagonal matrix. And this is quite nice. You can do SVDs for any matrix of rank R. So why is useful? Because, very quickly, 2 technical slides and after done, okay? The PLS can be writing like this optimization problem. So the covariance of XU and YV. What is XU and YV? XU is a linear combination of the X. YV is a linear combination of the Y. So U is your latent variable. So you'll try to find the U and the V, which are the linear coefficient in the linear combination, based on this optimization problem. And if you, after my talk, you can do it. Because you're just not to do. What you have to do is you construct your matrix. I have this, is better. Yes. This matrix, X transpose Y, X transpose Y, you multiply Y. You have M. Nice. And after what you do, SVD of M. And after, the solution of this optimization problem is just the first right singular value vector and the first left singular vector of the SVD, of the matrix I presented before. Done. The first step of the PLS is done. Okay, it's a little bit more technical, but mainly is this. Good news. Why useful? Okay, why useful? I don't remember. Okay, maybe I will know after. Okay, yes, because we have this nice theorem from Edgar and Hugh that this is the log rank approximation. So for any matrix M, if you try to find a matrix the closest to M of a rank R, is based, in fact, all of these guys are from the SVD. So in fact, just not to be technical, just to have the flavor to read my articles, is that if you solve this optimization problem, in fact, and you normalize the result, you get U1 and V1, which are from the SVD. So it's a shame because it's not me I have found this, it is Shen and Yang who connected the PCA to a least square minimization problem. So we can do the similar with the PLS, and in fact you can write like a regression problem. And as is a least square, you can add some penalties term to do some variable selection in your latent component. Technical. I will ask some question after if I don't have some question, okay? Oof. So in our unified algorithm, we have developed different sparse version of our PLS. Okay, I think I've done. Okay, now what is going on in the massive dataset context? So I remind you some nice definition from Emerson and Kane, which characterize a massive dataset, which is large if it exceeds 20% of the RAM, and massive if it exceeds 50% of the RAM. So what is going on with tall data in the PLS world? Tall data is the meaning that n is very, 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 very big. Okay, and for x and for y. So in fact, even if x and y is very, very tall, it's 5 minutes, perfect, I'm perfect on time. What I have to do, if the PLS is based on the SVD of x transpose y. But what is the dimension of x transpose y? Is a question. X transpose y is the dimension is p by q. So you have tall data. It's hard to deal with. You want to do a PLS. But in fact, the PLS is based on the SVD. So x transpose y is not big. So you can do a SVD of x transpose y and got your result of your SVD. But you need still to have the trouble to fit in memory x and fit in memory y, and to compute x transpose y. A simple trick is to do this by chunk, and it's just an equality. So x transpose y, you have x tall, y tall. You do some chunk, some group in row, and you can compute x transpose the first chunk transpose, multiply by y1, and so on, and add all of this. And this is equality. So x transpose y is difficult to compute on your laptop, but if you do some chunk, you can compute each chunk separately, or by a loop, or by a for each, or whatever, and you get x transpose y, and after, done. Okay? So we have done this in our package, some trick like this, and we use big memory to deal with the trouble of the allocation of the big matrix, and combine with the for each, and we managed to compute some regularized PLS and to add some sparsity, some gross sparsity, and so on. Just timing because I'm too it's okay. Okay. Not stop, come on. 2 minutes, good, perfect. Concluding remark, take-home message. So in our works, we have developed an unified algorithm. We include all the 4 kinds of PLS. And we also add a version of the PLS DA, so partially square for discriminant analysis. So it's the meaning that you deal with some categorical variable in the y part. We have deals with tall data by doing some trick, and we have parallelized the code, and now we have also some combination where n is big, p is big, q is big, many combinations. And the first package, SGPLS, is available on the ground, and SGSPLS and Big SGPLS is available on GitHub. Now, I'm sure you will be interested by read this nice article. And the last part is still on archive for a while. but maybe one day it will appear in the journal. I don't know. Thanks.
Thank you, Benoit. Questions? Presentation. Could you say something about the treatment of missing value within? Could you say something about the treatment of missing value within your PLS? If you use
Is a good question.
Thanks a lot.
And at this stage, we haven't included any function to deal with the missing value. So I think if we use the package just now, it will remove the missing value. So you do some imputation before, but normally the PLS, it will be there's a mechanism which can be used to deal with missing value. So it's a nice question, and it's just to push me to do it next time. Okay, thanks a lot to remind me this, because it's not the same, not the first time I got this question.
That's nice of advice.
Yeah, exactly.
Thank you for this presentation. It's very clear. My question for this package, now if you have a big dimension for Y, Q is very good, very big. What is the solution for this
If
problem?
Q is very big?
Yeah.
In our package, if P is reasonably okay, Q is big, or P is very big and P is reasonably well, it's fine. Any combination. And after the hardest part is when P is very big and Q is very big. We have limited to 50,000 for P and Q.
Second question, what is the difference of your package for multi-block PLS?
For?
Multi-block PLS.
We don't have a package multi-block PLS.
Huh?
We don't
no,
have.
No, you.
Not me, but...
No, it means comparison for this methodology by multi-block PLS.
Yes, we can extend to multi-block PLS. Yes.
Okay, more questions?
Can you just tell us in a few words how you can parallelize the computation, because it's iterative, and so I cannot see how you can...
Each step is iterative, but at each step you do the parallelize. So in fact, when you got your first component, your first pair of latent variable, you will be looking for to the second pair of latent variable. So you do some deflation step, and when it's done, it's like a new step of PLS with new data.
Yeah, but you parallelize by cutting the data into a chunk? No?
To compute X transpose Y. When you have X transpose Y, it's fine.